Okay, good morning, everybody. We'll get started. Hopefully, you have your welding shields on and your gloves, and you're ready to start welding. For those of you that um, couldn't either had difficulties with the link to the recording or haven't downloaded the recording yet, we started, I recorded this yesterday, the beginning of chapter 14, which is welded connections. Couple things that we need to note as we move down through the welded connections. Now, first of all, remember that we're not gluing the two pieces of steel together. This isn't like putting liquid nails on two 2x4s and squeezing them together. The welding actually fuses the base material and the electrode together. So, so those materials are fused together permanently. Welding has a lot of advantages. It's quiet. It's a smooth connection. Any place that you can reach with the welding electrode, which is a stick that's about, let's see if I can find my welding electrode. It's a stick that looks kind of like uh, a sparkler that you use with fireworks. So here's the welding electrode. This one happens to be shielded. This part up here is the shield has been pushed, scraped off, so you can see the metal. The electrode's not very big, but the electrode is what we're going to touch to the base material, and the welding electrode, and they're designated with E values and the grade of the electrode. Most of the electrodes, this grade of steel is higher than 50 KSI. And you can see down here the grayer part of the electrode. The electrode is shielded so that when you work with it in the field, the shield keeps you from getting getting shocked. Okay, so you'd always have a shielded electrode, and that way you can hold on to this. And there's an electric current that's running through it because on the back end you're going to clamp it to the welding machine or the lead from the welding machine. And the welding machine or the welder itself is nothing but a high price battery. So it just simply uh, puts a charge into the electrode. So that being said, the welds are all governed by the American Welding Society. Welded Structures by Blodgett is the best resource for welding and welded parts. Every good engineer designer has a Blodgett book, and I've got one in my office. There are a couple different types of welding, but most of the welding is arc welding. They don't weld stuff with torches anymore. I have a little torch, and I try to weld pieces of steel together in my backyard out on my driveway, and that doesn't work very good. I'm not a very good welder. I keep, like I was telling you on the recording yesterday, um, I keep asking for a welding machine for Christmas, and my wife swears I'll burn the house down get a welding machine, so I don't think welding is in my future. But here's what the weld looks like. This is the discussion about fusing the materials together. These are the base materials in green. Here's the weld, and the weld penetrates into the base material. The weld throat, this dimension, that'll be one of the dimensions that we give in the weld. The main dimension we give is the leg and the sides. So typically the face of the weld is at a 45-degree angle, and the leg size varies depending on how big a weld we're gonna design. So the welds look like this. They kind of have ridges on them because if you field weld a material and you move the electrode along and it fuses the material together, you actually hesitate a little bit. So there are a series of ripples in most welds. You can see it in these welds also. These are for stainless steel, and they've been polished, and a lot of architects prefer this welded look to bolting that connection. You can imagine if we were trying to bolt that gusset in between those two steel members, that we'd have bolts all over the place. And welding is much cleaner and easier, and it probably looks a little bit better in the long run. This is an X-ray of the picture that I just showed you, or the illustration. Here's the weld material from the electrode. These are the base material, and notice that the weld extends into the base material, and this weld right in here is both. It's a combination of the base material and the weld material, all fused together. So I went through the two types of welds. There are field welds. They're called SMAW welds, shielded metal arc welds. And there's what they look like. There's the electrode that I was just showing you. The electrode has an extruded coating on it. Then when you put a charge into the electrode, you set up a current, and you actually get an arc stream between the end of the electrode and the base material. There's the electric arc stream that melts the material together. So there's the base material and the arc stream, and you just move that right along the weld, and you can lay down the weld. The other type of welding is SAW, which is submerged arc welding. It's the welding that's done in the shop, so it's a different configuration. The electrode doesn't have to be extruded because this is a hands-free process. But since it's not extruded, the arc stream that's created creates a molten flux, and this molten flux is actually buried in a granular flux. So as this moves along, the weld gets solidified. So the flux tube is moving to the right, and all of this is moving along from left to right. We went through the recording the 5 types of welding inspection, just looking at the welds. Liquid penetrance is a cheap way to put a liquid dye on the weld and a powder, and you can see if there are any defects in the weld. That's what I use at my office. I've never seen anybody use the magnetic particles, the magnetized iron filings. Ultrasonic testing is what the labs will do if you hire a materials lab to go out and forensically investigate a weld. Typically, they'll use electrosonic testing. And electrosonic testing The sound is a sound wave machine. You set it up at the end of the member, and you send sound waves down the weld, and the sound waves, you can tell when the speed of the sound waves and where they hit a defect, they bounce back to the device, and you can see that on a cathode ray tube, so you can physically see any welds. We do that for rebar also. In a beam, if we want to see the rebars continuous in the beam from one end to the other, we can put the electrosonic testing device on the end of the rebar and see how far that sound wave goes and bounces back, so we can tell if there are any separations in the rebar. And then the most expensive procedure is to X-ray the machine, X-ray the welds. And it's very accurate and very expensive. I know by personal experience for the last 2 weeks, I've had a radiographic procedure done on me on numerous occasions in the last couple of weeks, and I hope it tells the doctors very accurately what's going on. Here are the classifications of welds. There are a lot of different welds. We're only going to do fillet welds and groove welds, and for the most part, we're going to do just fillet welds. So there's the fillet welds. These are groove welds. There's a fillet weld. These plug welds, as I mentioned to you before, are welds that are used for welding deck. So here's where we wanted to pick up. In order for you to talk to the welder, you have to put the proper weld symbol on the drawings. If you've ever seen your drawings come back from the engineer where there's steel involved, the weld symbols have a number of parts. This part right here is the actual weld symbol. So it's just a straight line, and then it's an arrow that points to where you're going to weld. The circle means you're going to weld all around. So if you've got a connection and you want it welded everywhere the welder can weld, and you put this circle on the weld symbol. The flag means that it's an SMAW weld, or that it's a field weld. And then these values that go on the line are actually the size of the weld. If the symbol is on the bottom side of the line, then you're welding on the side of the connection where the arrow is. If you add a size on the top of the line, then that tells the welder he's got to weld it on both sides. The symbols for the welds, we're going to deal with fillet welds all the time. So our symbols will typically be triangles. There's the plug or slot welds. Back welds are welds that are recessed back in the steel so that you can cover the weld with caulking. The symbols, this flag, as I said, means field weld, contour, flush, and convex. I don't have any idea what that is. These are all of the groove weld symbols, and I don't know that I've ever designated a groove weld. How to do that? Some of the they look like brands if you brand a cow with. So there's what the weld symbols look like. The code, 2018 IBC under welding, says welding inspection shall be in compliance with AWS. That's the American Welding Society. D1.1 is the document, and it's a fairly complex document, but it tells you how the inspections for welding is done. Now, in accordance with Chapter 17 of the code, all welds have to be inspected. So you have to have a third-party inspector go out and do an inspections of the welds, and he does that with one of those 5 procedures. So let's see, how strong is a weld? How do we calculate a weld? Well, LRFD design method requires that the factored load effect not exceed the design strength of the weld metal or base material. What a good idea, okay? So the strength, the design strength of the weld metal or the base material better be greater than the factored load, or it don't work. So there's the factored load, and that would be like P sub U is a factored load. Has to be less than the resistance of either the weld or the base material, whichever is less, and it has a resistance factor, so there is a phi factor for a weld. So if I'm welding 2 pieces of steel together in order to find the strength, for instance, the strength of this weld at this plane is based on the shear strength of this material. On a plane at 45 degrees through the weld material will govern, and at a plane in material 3, material B, that would govern govern the strength of the weld. So we're going to calculate the design strength of the weld based on the throat area, and the throat area was the picture that we saw before. Since failure of the weld metal occurs on the throat area, the nominal resistance strength of the weld metal can be written as, there's the nominal strength, R sub n is equal to A sub W times F sub W. The design strength, you have to factor that by the phi factor, the resistance factor. And in this equation, A sub W is the effective cross-sectional area of the weld. So that's the leg size times 0.707. 0.707 is the sine of 45 degrees. So that's the throat, the leg size of the weld. Wait, I'll get to it. Here it is. So there's the leg size, and we're going to give the leg size on our drawings. And the failure plane goes at a 45-degree angle. So if we know the leg size times 0.707, we get the effective throat area. So F sub W is the nominal strength of the weld electrode. And as I said, the weld electrodes have different strengths. EXX is the ultimate tensile strength of the weld electrode, and that's the EXX in this equation, and it's factored by 0.6. So we take 60% of the strength of the weld electrode. We rewrite this equation, and now the nominals, the design strength, phi times R sub n is phi times the area of the weld times 0.6 times the strength of the electrode. Okay. Most of the weld electrodes are 70 KSI. So 70 KSI is the typical strength of the weld electrode. So for a typical weld electrode, you can find the nominal strength of the weld as A sub W, phi is 0.75, 0.6 is what we factor the electrode, and the electrode is 70 KSI, so that comes out to be 31.5 A sub W. That's the basic equation for a weld, the design strength of a weld using an E70XX electrode. For the base material is the design strength of the base material is phi times F sub Bm for base material, times A sub Bm, which is the area of the base material. So the nominal shear strength of the base material is what we're interested in. It's 0.6 times F sub Y. Then A sub Bm. Remember the cross-sectional area when we weld things together, we always use the gross area. There ain't no holes. We're not going to use a U factor because we're welding two plates together, so we use the gross area. Once again, the phi factor for the base material is 0.9. There's 0.6 F sub Y. That's the nominal shear strength of the base material. A sub G is the cross-sectional area. And you can rewrite this equation as 0.54 times F sub Y times A sub G. So now calculate the design strength of a 1-inch long fillet weld with a leg size of 1/16 of an inch. I'll plug into that first equation. The nominal strength is 31.5 times the area of the weld. It's a 1/16 inch weld times 0.707. It's 1 inch long. That's 1.392 kips per inch. Okay. You'll notice on the canvas there's a quiz down at the bottom. It's multiple choice. And I believe the first question is, what's the capacity of an 1/8 inch weld that's 1 inch long? Well, if we had an 1/8 inch weld, we'd simply put an 1/8 of an inch in here, and we'd come up with the strength of the weld. This table is not in your text. It'll only be in your notes. But at one time they had this table in the text, and it's pretty exotic. They figured out the weld size and the strength of each different weld size. So like I said, that first question, I think, on the quiz is what's the capacity of a 10-inch long, I think, a 10-inch long 1/8 inch weld? Well, it's 2.78 kips per linear inch. So multiply that times 10, and that's the capacity of the weld. So if I had a 1/8 inch fillet weld and it was 10 inches long, and it carries 27.8 kips. Pretty good, okay? So the design strength of the base material, well, the design strength for the base material, we need to calculate it and see 0.54 times F sub Y times A sub G. There's 0.54. The F sub Y is 36 KSI. It's grade 50 steel. 1/16 times is the thickness of the material times an inch. So it's 1.215 kips per 1/16 of the material thickness. Now, before we do another example, just quickly, the second question on the quiz asks you if you're welding two pieces of plate together, and I think one piece is 3/8 and one piece is 1/2 inch. The question is, what's the maximum size of the weld that you could weld those two pieces of steel together? Well, obviously, you can't use a weld that's 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 thicker than 3/8 of an inch because the weld material would dribble over the edge. That it would be totally impossible to do. So you could physically you could get a weld if you can imagine putting a 3/8 inch plate on top of a on top of a on top of a half-inch plate, and that's what we got. And yeah, that's what we have in both of the homework problems. Let me put up. I'll just put them, set them here on my document reader.
Professor, while you're doing that, I had issues accessing the video. It said that I did not have permission to view it. This is
Oh, really?
Yeah. I don't know if anyone else had those issues, but
sometimes, yeah, sometimes it has. There's a timestamp or something, and sometimes the video. What I may have done. Um, what I may have done is I may have set the time of the video for an hour. So when I was sitting here yesterday doing the video, it may have not allowed permission to view the video after that time period expired. So what I'll do is I've got the link to the video, and I'll just email it to all of you so you can have the link to the video in an email, and that way you can look at it. Okay.
okay, sounds good. And did you by chance go over homework 10 in the video? Because I know you had talked about how we would at least touch base on it in the next class. So I don't know if that was something you did in the recording.
I did not. No. Let's look at homework 10. Okay, here's homework 10, and it says there's a truss member, two C12 by 25 members. So there's the C12 25, two of them on either side of this gusset. It's just kind of like the connection, as we were mentioning Monday, it's kind of like the connection, if we turn it like this, it's the connection at the gusset of the bracing on our building that runs at a 45-degree angle. But this is to find what the maximum piece of view is for those two C1225s. The gusset plate is an inch, and it just asks how many A325 bolts with the threads excluded from the shear plane are required to develop the full tensile capacity of the members if they're used in a bearing type connection. Okay, sounds pretty easy to me. Okay, if we got a bearing type connection, maybe the best way to attack this is to go back to the example problems in chapter 12. So let me get chapter 12 up. Okay, here we go. And when we were doing the bearing type connections, here's example 12.1. The bolts are 7/8 inch, 325 bolts, and there they are. And the question homework number 10 is done just like this example, except that we don't know how many bolts there are in a row, and we know what piece of view is. So that's the difference. That's the difference in this example problem and the homework problem. The steel is the same. The threads are excluded from the shear plane. And this question was, how much load would 4 bolts carry? And here's the gross section calculation, and here's the net section calculation with the number of bolts. So what you'd start off with in homework number 10, you know what piece of view is because you can find the tensile strength of a C 12 by 25 channel. Okay, so go to the steel manual, find the area of a C 12 by 25, and find out from the area what the gross area is. You can find the capacity of the 12 by 25. So just like this example problem, you're going to figure the gross section on the yielding of two 12C 12 by 25s. And I think their area was like 7.25 inches.
It's like 7.34.
Okay.
So we do that by 2?
Multiply that times 2 because you got 2 of them. Mm-hmm. And so this piece of N would be 36 KSI times this value in parentheses is the gross area, so that'd be 14.68 square inches, and that gives you the yielding on the gross section. Multiply that times 0.9, and that gives you the design strength of the 2 channels. Now the tensile rupture strength is calculated exactly the same way. Remember now that the tensile rupture strength for the 12 by 25, the bolts, there are 2 lines of bolts. So
that was going to be one of my questions. If we can go ahead and assume that there are 2 lines of bolts because we don't know how many bolts. Okay.
Yeah, there are 2. Yeah, that it shows. Yeah, my drawing it very lightly shows the 2 rows of bolts, and so you got 2 rows of bolts, and we can put in 4 bolts or 6 bolts or 8 bolts, whatever it figures out to be. That's what the question is. So with that, the number of bolts for the design of the connection doesn't make any difference because the tensile rupture strength, remember, is a plane that cuts through the 2 bolts. So we've got the gross area of the 2 channels, which is 14.68 square inches. So this is 14.68 square inches. They'll have 2 7/8 inch holes through them, and the thickness of the flange of a C 12 by 25 is the value that goes right here for the thickness. We got the number of holes times the thickness. So when you look in the steel manual, right next to the area is how thick the webs are, and that's where the bolts are located. So say the webs are 3/8 of an inch thick, that would be 3/8 of an inch, and that gives you the net area. We're going to use, it says, assume in the problem that U is 0.85 because all the parts are not connected. The flanges of the C 12 by 25s are sticking out in the air, so they're not connected. So we could go through that design analysis, but screw it, we'll use U as 0.85. So 0.85 times the net area gives you the P sub n. So once you have the P sub n, and here's the design strength, multiply that value times 217.5, and we're going to design the number of bolts, okay, for the lesser of those two values. Because we know we could put in a zillion bolts in this connection, and well, the strength of the C12 by 25s control the capacity of the connection. So all we're trying to do in this problem is figure out how many bolts gets us to that lowest lowest strength of the C12 by 25s. So that being said, now we can figure out the number of bolts. So we can solve this equation right here for the number of bolts. In this case, for this problem, there are 4 bolts. Well, for the homework problem, we don't know how many bolts there are, but we do know that L sub C, which is the spacing between the bolts, is 3 inches. And it's 2 inches to the first row of bolts from the edge. So we'd be 3 minus a half an inch, or the same thing, 3 minus this bolt is 3 inches in. Ours is 2 inches, so 2 inches minus half of a 1 inch hole would be 1.5 inches. So that's the value that would go right here. The smaller of those goes into this equation. And now we know everything except the number of bolts. So we got to solve for the number of bolts in a bearing connection. So we know 1.21. L sub C we can figure. The thickness of the web of the C12 by 25 goes in here. F sub U, it's grade 50, right? Grade 50 steel. A325, so the F sub U is 50. And the number of bolts is X. That has to be less than this value, so you evaluate this this inequality, and whichever if this value, if the left-hand side is less than the right-hand side, then that's the value that you're going to use, except your answer is going to be, you're going to have, this is the X where the 4 is in this equation. We're going to have an X there for calculating the number of bolts. So when we get down here, we've got 0.75 times times this value, which now still contains an X because we don't know the total number of bolts, but we can find them right quick by taking the value that we need, the phi times R sub n, is the lower of these values from the gross section or the tensile section. So we got that number, and we got that number. So, so that will give us the R sub n that we can put right here and solve for the number of bolts. Okay.
If the number of bolts that you have was like a high, so I have like an odd number with like a 0.8.
Okay.
Should I round up to an even number, or should
Sure.
I? Okay.
Yeah, exactly. Yeah, we want 2 rows of bolts. We don't want them staggered. Perfect. Or any of that fancy stuff. Okay. So if you come out with 9.8, then you put in 2 rows of 5 bolts.
Okay. Thank you.
All right. See, now if we weld that connection, it'd be really easy to do because we know what the strength of the 2 C channels are, and we simply come up with the weld side. So, so let me get back to Oh, I know. I was going to look at the document reader. Here's homework number 11, and the only thing I wanted to show you from number 11. Now, first of all, you have to figure out how long the fillet weld needs to be to get 173.5 kips of tension. And the two plates that we're welding together, as you can see, are half-inch plates. So if they're half-inch plates, the answer to the second quiz question is, if I'm welding together a 3/8 inch plate and a half-inch plate, what's the maximum size of the weld? Well, the fillet weld that goes right here and right here, the size of that weld, although theoretically it could be 3/8 of an inch. We don't ever size the weld that large. The weld will always be a maximum of a 1/16 of an inch less than the thickness of the thinnest plate. So in this case, we got two half-inch plates. The biggest the weld could be is 7/16 of an inch. So I could figure out what's the strength. This isn't very difficult to do. What's the strength of a 7/8 inch of a 7/16 inch weld? Well, I can tell you because we've got that in our tables. In the table I was just showing you. Here's the magic table. So I need 173.5 kips, okay? Keep that number in your head. Now, what length and size of weld would be required to carry 173.5 kips? Well, as you can see, the length of the welds per inch, if we have the maximum size weld is 7/16 of an inch, and it carries 9.74 kips per inch. So if I take 173.5 and divide it by 9.74, I got it. So for a 7/16 inch weld, that means that 173.5 enter 9.74. Right. That takes 17.8, we're going to say 18 inches of weld. Okay? So if I got the two plates, I need 18 inches of weld. How do I configure that 18 inches of weld? Figure it like this. Right? Let me get the document reader. Okay, I got one plate like this and the other plate like this. Okay, here's the force is 173.5 for a 7/16 inch weld. Okay, it carries 9.72 inches, 9.72 kips per inch. So I need 18 inch long. The length of the weld is 18 inches. So up here in the configuration of the weld, I wouldn't try to put a weld 18 inches long here and lap those two pieces of steel by 18 inches just to get a weld in. And usually we want the welds to be symmetric. So I could put in a weld like this and like this, and that weld would be, I'll make it 9 inches long. I got 9 inches there and 9 inches there. I got the 18 inches. Or, and this is the fun part of doing welds, or I could weld like this, okay? And this plate, and the homework problem, forget the smaller plate, is 10 inches. So if this dimension is 10 inches, and I weld on the end, I got 10 inches of weld, so I could put 4 inches of weld up here, 4 inches of weld down here, and I got a total of 18. The capacity of the weld is the same in shear as it is in tension. So the bottom line is I want 18 inches of weld. So that means that I could also put, and I'm just drawing these on here, I could put 7 inches of weld down here, 7 inches of weld up here, and then I could turn the corner, Now I got 14, I need 18 with a 2-inch return. So that configuration would work also. So in these welded problems, the right answer is the total length of the weld. The configuration of the weld can vary. Oh, wait, I don't want to use a 7/16 inch weld. I want to use a 1/8 inch weld, okay? Aha. So if I want to use an 1/8 inch weld, go back to the super duper table.
Professor, why did you change your mind on that?
Change my mind.
1/8 instead of 7/16.
I can put any size weld I want up to 7/16. Okay? And my welder says to me, hey, I'd like to put down 1/8 of an inch weld because that way I only have to make one pass at the connection. Remember, I can get 1/8 of an inch thick weld with just passing the electrode one time. To do the 7/16, I'd have to do 3 passes of the weld, and I'm lazy. I only want to do 1. So the point I'm trying to make is you can use 7/16 or 3/8 or 5/16 or quarter or 3/16 or an inch or a 1/16 of an inch weld. Any of those will work as long as you got the right length of weld. Okay, so if I want to use a 1/8 inch weld, its strength is 2.78 kips per linear inch. Okay, 2.78. So remember that number. And for the 1/8 inch weld, it carries 2.78 kips per inch. And if I take 173.5 kips and I divide it by 2.78 kips per inch, then, so you don't always have to use the maximum size weld. Any weld that's smaller than that maximum size is still good to use. And now the weld would be 173.5 enter 2.78 divide. The weld would be 60 inches long, 61 inches. So now the length of the weld is 61 inches. So that means I need to lap the steel on there further and say I need, it's 10 inches wide, so I need 51 more inches. So I'd have 25.5 inches up here, 25.5 inches down here, the 10 inches on the end. That gives me a total of 71, and that would work. Don't have any issues with that. The length of the weld, is could be 25 inches. Now, right above, I'm going to put the weld symbol. First of all, I'm going to weld all the way around this member, so I put a circle in there. The arrow would go like that, right to the member. This triangle means it's a fillet weld, and if we stick with the 7/16, we have 7/16, and then the weld symbol up here would be 7/16, because I want to weld both sides. Okay, for the channel, I'd want to weld on both sides. For the plates, I don't. So I don't have anything on the other side. I got a 7/16 inch weld. Now, out here, in this part of the weld symbol, I can give instructions to the welder if there's something special. For instance, I don't need to make the welds continuous. All right? If I have a plate configuration like this, I can put a 1-inch weld and a 1-inch weld and 1 inch and 1 inch and 1 inch, or whatever I want. And in this space right here, I'd put 1 inch at 2 inches on center. So now I'm putting a 7/16 inch weld 2 inches apart, and there are 1, 2, 3, 4, 5, 6, 7, 8. Say 8 of those at 1 inch wouldn't give me the 18 inches that I need, so I'd have to put in more. But for illustration purposes, on the back side of that weld symbol, that's what tells you, or tells the welder, hey, I need to, put in the welds in 1 inch lengths, 2 inches apart. Okay. So that would, if I made the welds, in fact, for this problem, if I made them 2 inches long at 1 inch on center, and I got 3 here and 3 here and 2 there, that's 8. So I'd get 8 times 2 is 16. I almost get to my 18-inch requirement. And that would be acceptable also. So there are a variety of ways you can designate these welds and calculate the welds. Okay? So there's really no right answer other than having the right total length of weld. So you'll see in the homework problem, in the example problem that we're going to do next time, that's in the text, you'll see that we're going to just pick a 5/16 inch weld because it's more than a 16th less than the thickest material. We're welding the thickest base material. So that's good. We could use that. If we don't like it, we could pick a different size weld or a different length weld. Okay. Try to make the welds symmetric like we did here. All right. Okay, I'll go. I'll send you all a mass email, and in the email will be the link to the Microsoft streaming video that you don't have access to right now. So I'll just email it all to you here right after my next class. So you'll have it right around noontime. Okay.
David.
All right. All right, that's welds. That's welds for today. We'll finish welds on Monday, and I'll give you the exam for chapters 12 and 14 on Monday, and it's the exam on bolted connections and welded connections.
Professor?
Yeah.
I have a question. So you said that the maximum weld size was 1/16 of an inch less than the thinnest member, correct?
Correct. Yes.
So that doesn't matter. It wouldn't change depending on having different members. You don't have to have like two symmetrical members or the same size.
No. Pieces you're welding together, in fact, most of the time they won't be the same size because you'll have a plate coming from the column and then you're going to weld a beam to that plate, and it would be just a coincidence if the thickness of the web of the beam and the thickness of that plate were the same. So when you calculate the weld, you take whichever is the thinner, and that's the maximum size of the weld. So it would either be that plate or the web of the steel beam that's attaching to it. So it would be unusual to have two plates or pieces that are the same thickness. Most of the time they won't be.
Okay. The reason I asked that question, I took the quiz and it said I got the answer wrong. So I don't know. Do you check those quizzes? Like, do you like double?
Oh, of course, yeah.
Okay.
Yeah. What did you say? What did you say was the answer on the quiz? 5/16?
No, I said it was 7/16.
No, one of the plates is 3/8.
Oh my goodness!
Uh-huh.
I this is what I did.
Yeah, see, I got you. 3/8 inch plate. Now you couldn't put a 7/16 inch weld. That weld is thicker than the thinnest plate. So you violated the law of go to jail, do not pass go, do not collect $200. Okay.
I realize that. Thank you so much.
Okay. See you all Monday.
See you Monday.
Okay, bye-bye.
Hey, Professor, before you log off, I have a quick question for you.
Yeah.
Hey, I'm just like Abraham. I ended up taking the quiz, and just as I hit submit, you mentioned that the welds could be 1/16 less than the largest member.
No,
I believe
the thinnest member.
I'm sorry, the thinnest member. I apologize.
Yeah.
So I put in 3/8 of an inch because I thought that because earlier you said that the width of the member is the width of the weld.
Well, the weld has to be. It could be 3/8 of an inch thick, but practice and the code says no, you can't do that. The weld has to be a 16th, maximum of a 16th of an inch smaller than the thinnest material that's being welded.
Correct.
They do that for a reason because, if you're using the 1/2 inch material and you say, hey, the weld could be 7/16 of an inch, that in fact is wrong because that's even thicker than the 3/8 inch plate.
I see.
Yeah.
I see. So there lies my question. What are the chances that I may receive another attempt on this, or should I just roll with the?
I think it was it not multiple attempts? If it was,
No,
what I'll do is I'll edit the input values for the quiz, and I'll change the due date, due time to noon, so you can go ahead and change it and resubmit it. Okay.
That would be awesome, Professor.
You got it. No problem.
You're the man. I really appreciate that. Yeah, I hope everything went well with your procedures this week, and look forward to meeting on Monday.
All right, let's see you Monday. Thank you.
Take care and have a great weekend. Bye-bye.
You too.